Let's go back. So those are all factors that affect the heart rate. So we've only been looking at this side of the equation. Factors, which are neurons, hormones, intrinsic and extrinsic mechanisms that can affect the heart rate. Now, coming back to our equation, we want to think about factors that can affect the stroke volume from this point going on. So the stroke volume is going to be the amount of blood ejected from the ventricles, especially during phase 3. And so we're going to look at factors that can affect that as well. Now, the factors would be the contractility, how hard those ventricular cells are working, the end diastolic volume, how much volume was filled from the venous return from the atria down into the ventricle to begin with. What does the end diastolic volume look like? And then the afterload. Afterload implies how much volume / pressure exists beyond the heart. What does the resistance, the peripheral resistance look like? Those are things that are going to affect how much blood can actually leave the heart. The force of contractility, the amount that was filled to begin with, and the pressure and resistance that exists outside of that ventricle. Let's look at these one at a time. So we're going to start with the first one, which is the ventricular contractility. And basically, the principle is the more forceful the heart can contract, the more volume it can expel. So the forcefulness of the ventricular contraction dictates how much stroke volume can actually leave the ventricle. And this is going to be under the sympathetic control because, as I keep reiterating, the contractile cells of the ventricles are only under sympathetic control. They have no influence from the parasympathetic system. The parasympathetic system only influences the SA nodal and AV nodal cells or the pacemaker cells. So the sympathetic system is the only system that can control the ventricular contractility. And the mechanism of how this takes place is norepinephrine, either hormone or neurotransmitter, binds to beta-1 receptors. Cyclic AMP is released by way of the second messenger system, and that results in 4 responses. All 4 of these responses ultimately translate to increased contractility. So what are those 4 responses? So the 4 responses are, they're going to increase or augment the time that we spend with calcium channels open. And if we think back to the source of calcium for cardiac contraction, we know that this comes from outside of the cell. We know that, especially in contractile cells, there's that plateau phase that we discussed, where the membrane potential intentionally stalls to allow more time for calcium to get in, which can increase cross-bridge cycling and increase the strength of those contractions. So augmenting the time that calcium channels are open translates to more contraction or more forceful contraction. The second one is increasing the calcium release from the SR. This is the second source of calcium that drives cardiac contraction. So increasing the calcium from the extracellular fluid, but also from the SR, both of those things increases the contractility. Thirdly, increase the myosin ATPase rate. That is how fast those myosin ATPase or the myosin heads can actually make cross-bridge cycles and break cross-bridge cycles. That is the speed of the contraction. So that can also increase the contractility. And then fourth is the calcium ATPase activity, which is what clears the calcium back into the SR and back to the extracellular fluid to allow the cardiac muscle to relax. So we've said this many times before. If we can increase the rate of relaxation, we can increase the rate of contraction, and we can increase the forcefulness of contraction over time. So these are the 4 events that are triggered by the sympathetic system on the contractile cells, the ventricular contractile cells. Okay, let's look at some of those events here just to illustrate this. So we start with the same sort of precursor events, beta-1 receptors binding norepinephrine or epinephrine, cyclic AMP being released, and cyclic AMP resulting in those 4 events. 1, the duration of time the calcium channels will spend open. So we're going to delay or prolong how much time these channels are open so that more calcium can come in. 2 is to increase the opening of calcium channels on the SR. So this allows more calcium to come from the ECF and from the SR. 3 is the myosin ATPase activity. How fast are the myosin heads forming and breaking those cross-bridge cycles? In other words, what is the total amount of contraction that's happening based upon the myosin heads? And then 4th, the calcium ATPase. How fast are we able to clear that calcium by pumping it back into the SR, and we can have another contraction much faster if we can relax the muscle cell much faster. Okay, so the same 4 events that we discussed on the previous slide, which all help to increase the ventricular contractility. So if we look at the amount of force or tension that's generated when the myocardium is at rest versus when the myocardium is being heavily influenced by the sympathetic system, we're going to see that we can have more force produced in a shorter amount of time when the sympathetic system is engaged because of those 4 mechanisms we described, versus less tension over a longer period of time when the myocardial cells are at rest, right? When they're not as influenced by the sympathetic system. So notice that there's no parasympathetic. I keep reiterating this because you're going to see this on the exam, and this is going to be a really important concept. Notice that there's no parasympathetic curve here because the parasympathetic system does not influence the ventricular contractility. It does not at all influence the contractile cells, only the SA node and AV nodal cells. So the 2 options for the ventricular contractile cells are rest, which is no sympathetic involvement, or exertion, which is when we do have sympathetic engagement. Okay, now just reiterating this, not significant, little to no influence on the contractile cells coming from the parasympathetic system. Looking at the hormones here, hormones will do the same thing that the neurons do. Binding of epinephrine as either form will result in the 4 events that we discussed. So it's going to have the same effect as a hormone as it does as a neurotransmitter. And then other types of hormones that can play a role on ventricular contractility are thyroid hormones. So T3, T4, we know are going to be just metabolic hormones. They're going to increase all types of functions, the sodium potassium pump rates, the calcium ATPase rates. And so overall across the board, thyroid hormone can increase contractility. Insulin can also do this, and glucagon. So these are other hormones we've discussed in the endocrine system as well. Now let's talk about the end diastolic volume, which is the second major factor that can increase or regulate rather the stroke volume. First was ventricular contractility. Second is the end diastolic volume. So the end diastolic volume is going to follow the Starling's law. And the Starling's law is the autoregulation example that I gave earlier. If you increase the stretch of cardiac muscle fibers, you bring them closer to their optimal length, and you increase the strength of the contraction that they're then going to sort of recoil or contract with. So when we think about the optimal length, in skeletal muscle, muscle is typically at its optimal length when it's suspended across 2 joints in the body. The cardiac muscle, on the other end, approaches its optimal length the more it gets stretched. So optimal length means 2 separate things for skeletal muscle, which is kind of in the middle, versus cardiac muscle, which is when it's really stretched out. So stretching of the cardiac muscle increases the strength or force of contraction, and this is called the Starling's law. That is to say that if I increase how much blood is returned to the atria and how much blood is filled down into the ventricle, I'm going to increase the stretch of those muscle fibers. And as I increase the stretch of those muscle fibers, they are going to increase their force of contraction, which means more blood will be ejected as long as more blood is filled. So increase in venous return translates to increase in stretch, which translates to increase in the strength of contraction, which results in increased ejection or increased stroke volume. All right, and that is the Starling's law. So just to illustrate that, here's the stroke volume and then the end diastolic volume. So when the cardiac muscle is in its relaxed state, so it's not stretched in this instance, it can generate X amount of volume based upon the amount that has been filled. So this is the stroke volume based upon this amount of end diastolic volume. If we increase the stretch, if we increase the length of the sarcomere by filling more volume and causing those muscle fibers to stretch to approach their optimal length, now we're going to see that we can have more volume ejected, even with the same, or we can have more volume ejected, excuse me, with a greater amount of end diastolic volume. So now we have filled more, end diastolic volume is greater, and we're going to eject more because we have a stronger force of contraction, because we have stretched the sarcomere and the muscle fibers toward their optimal length. And so this is the Starling's law or Starling's curve. All right. Another way to sort of illustrate and represent this, if we have our initial curve, so this is our resting state, and this is for a set end diastolic volume. If we were to increase the sympathetic activity, we would increase the stroke volume even for the same end diastolic volume, okay? If we were to decrease the sympathetic activity, we would decrease the stroke volume, again, even for the same end diastolic volume, because as we increase the sympathetic action, we increase those four mechanisms that we talked about. And so doing so, even if it's the same amount of volume, the cells are going to be working harder and they're going to eject more, which is going to increase our stroke volume. And so this is another way to appreciate Starling's law. Now, the factors that affect the end diastolic volume would be things like preload. Preload is the blood coming into the heart. So afterload is pressure beyond the ventricle, beyond the arteries. Preload is pressure that's coming in. So preload is going to be determined by the amount of time the heart spends filling, how much of that blood can actually spill down into the ventricle, the amount of atrial pressure, how much pressure exists in the atria to help that end diastolic volume, to help that volume spill into the ventricle, and then central venous pressure is how much pressure exists in the veins that are returning to the heart. So the superior vena cava, the inferior vena cava, how much pressure exists in those vessels, which will influence more blood to come back into the heart. So those are the things that will influence preload and therefore influence stroke volume because they influence end diastolic volume. All right. Another thing is afterload. Afterload also affects end diastolic volume and will therefore affect stroke volume. And afterload is the pressure that exists in the aorta during ejection. So what is the resistance in the aorta look like? Because if we have a very narrow aorta, which means we have a lot of resistance, we're going to see less stroke volume able to leave the ventricle because there's just more resistance. If we have less resistance in the aorta, less pressure in the aorta, we're going to be able to eject more and have a higher stroke volume. So afterload also affects the end diastolic volume and therefore stroke volume. All right. Now looking at the illustration here, this is just showing factors that affect the stroke volume. So first is the end diastolic volume. End diastolic volume is affected by venous return. If we have more blood coming back to the heart, we're going to fill more into the ventricle. We're going to be able to eject more based upon Starling's law. The second factor, the contractility. If we have sympathetic system engaged, we have those four mechanisms we described, we're going to have more ventricular contractility, we're going to have more volume ejected or more stroke volume. And the third is the afterload. If we have a decreased arterial pressure, and we refer to this as decreased peripheral resistance or obstruction to flow in the arteries, if we decrease that, we're also going to see more blood be able to leave the ventricle, and that's going to be increased in stroke volume. So these are the three factors that affect stroke volume and will therefore ultimately, if we think back to our equation, affect the cardiac output, which is a product of stroke volume.